Okay, so in this next lesson, we are going to introduce this concept called a logarithm. So here is the best way I can describe this to you. If I gave you a simple equation, something like this, and I asked you what the value of x was, I would say that every single one of you is good enough number sense wise to figure out that that x has to be a 2 because 3 squared is 9. Now, I can continue to do that. What if I told you that this was 3 to the x equals 27? Again, number sense wise, we're probably all good enough to figure out that now that x has to be a 3 because 3 cubed is 27. The issue becomes, what if I ask you a question like this? 3 to the x equals 10. How do I figure out what x is if I don't know, or if I know that this power isn't going to be a nice, neat whole number or a nice, neat rational number, like a fraction? So that's where we introduce this concept called a logarithm. So what we're going to learn is that I can rewrite this in a different form, in log form. Right now, it's an exponent form. And I can write it in log form so that I can then use a calculator, whether it's graphing or a scientific, to evaluate what that value of x is. So here's how the forms work. If I have an exponential form, something like b to the x equals y, or in our case, 3 to the x equals 10. Notice how they look almost identical. I can take it and I can write it into log form. So here's how it goes. The exponent base that you have, the 3, is your log base. Notice this says log base b. So if I want to write this in log form, I would first write the word log, and that exponent base 3 becomes the log base of 3. The number on the opposite side of the equal sign, in this case the 10, goes inside the log. So that's read as log base 3 of 10. And the power that's up here that I'm trying to figure out becomes on the other side of the equal sign. So this here is the exponent form. This here is the log form. And mathematically, they actually mean the exact same thing. They're just in different forms. Exponent and logarithm. There are some different properties of logarithms that are becoming very important, and here's why, and here's the basis of them. Whenever I see something that looks like this, this actually means mathematically 3 to what power gives you 10 as an answer. So again, a logarithm means 3 to what power gives me the number 10. So when we start talking about these different properties down here, one of them being this. If I ever do a log of 1, whether it's log base 3, log base 5, log base 10, and so on, anytime I take the log of 1, I get 0 as the answer. So why is that? Well, if I do something like log base 5 of 1, and I'm trying to figure out the answer, think about this to yourself. This is asking you what power of 5 gives you 1 as the answer. So I want you to think about that numerically. What number, what exponent on any base gives you 1 as the answer, and that answer, that number, is 0. So that's why if I take the log base 5 of 1, or the log base 2 of 1, or the log base 10 of 1, and so on, that's why you always get an answer of 0. The next property is if you ever take the log of the same number. So something like log base 5 of 5. That's always going to give you a value of 1. So why is that? This is asking you 5 to what power gives you 5 as an answer. So in exponent form, you're actually asking yourself 5 to the x power equals 5. What does x have to be? X would have to be the number 1 because 5 to the first power gives you itself. You can also look at this as they cancel each other out, which is something that's going to become very important as we move through the rest of this unit. They cancel each other out and all you get is the power 1. Two other things, if you look at your calculator, if you have a scientific or a graphing calculator, what you're probably going to notice is it has a couple of log buttons on them. The two log buttons, if you have a calculator that looks like mine, there's an LN button and there's a log button. Those two buttons don't allow you to put in whatever log base you want. They only allow you to put in what's called common log, which is log base 10, and natural log, which is log base E. So if you're trying to evaluate something like log base 3 of 10 in the calculator, there's a trick that you need because you can't just type that in the calculator. Unfortunately, if I go to the calculator and I just do log and I type in 10, this doesn't mean any base I want. This means log base 10 of 10. So the calculator is going to tell me this answer is 1. I can't use the natural log and do for 3 because this means e to what power gives me 3, not this question that you're being asked here. Now there is a way around this and we'll talk about that way around it tomorrow. Most of the problems that we're going to talk about today, you're going to be able to evaluate without one of these. So I'm going to get rid of this right now. So moving on to the next page. We're going to talk about how to take things and switch their forms. So it becomes very important that we're able to do this. So we're going to switch from exponent form into log form. So remember, anytime I'm looking at an exponential, if I have an exponent base of 2, that becomes log base 2. The number on the other side of the equal sign is what goes inside the log, and the power is what the log is equal to. If I take my log expression and I put it in exponent form, first thing, if I have a log base of 4, that becomes exponent base 4. The number on the other side of the equal sign, a log is always equal to the power, so 4 to the 0. And then the inside portion of the log goes on the other side of the equal sign. 4 to the 0 equals x. If I continue on my exponent base here, I would have a log base 12 because the number being raised to a power is 12. Other side of the equal sign goes inside the log. The power is always what the log is equal to. Switching into this form, log base of 1/4 means that I'll have exponent base of 1/4. The log is always equal to the power, so that becomes the power. What's inside the log goes on the other side of the equal sign. So it's going to become very important as we move through this unit that you're able to switch back and forth between forms, and you'll see why when we get into the last part of this lesson, which is involves inverse functions. Okay, so now let's talk about all of these. These are all logarithms that I would expect that you could evaluate without the use of a calculator. Okay, so let's talk about how I would look at each one of these. Now let's talk about what each one is asking you. If this is asking you log base 4 of 64, I'm asking you 4 to what power gives you 64? Now some of you might be thinking in your head, oh, that makes sense. My answer would just be 3, which you'd be correct. For those that can't figure out or work that way, what I normally do with this is I write it in exponent form. Since your mind has been working with exponent form for much longer than log form, it makes sense that your brain is going to think better when you're talking about it in power form. So let's write this correctly in power form. That base 4 becomes the exponent base 4. You don't know what the power is because you're trying to figure that out. And the inside of the log becomes the 64. So now that you're looking at this exponential equation, this is one of those easy ones that I started off the video with, like 3 to the x equals 9, or 3 to the x equals 27. This is one that I would expect you could figure out, and that you'd figure out that 4 to the 3rd power gives you 64. So that's why x equals 3. That's why the answer for my logarithm is 3. Coming to the next one. This one's a little bit weirder because we've got a decimal in here. So what I want you to think about is that decimal is actually what in fraction form? Now reading this, that's 2/10. So if I write that as a fraction, 2/10, it reduces to 1/5. So this is actually asking you log base 5 of 1/5. So I think it's probably easiest if we look at this and we write it in exponent form. And so what I'm going to do is take that 5 base, raise it to a power, and it should equal the inside portion of the log. So what this is actually asking me is 5 to what power gives me 1/5. So in order to change a whole number into a fraction, I want you to think about what kind of power would you have to use. The only kind of power that changes something from whole number into fraction or vice versa is a negative power. So in order for this 5 to just simply change into 1/5, x would have to equal -1. So log base 5 of 2/10 equals -1. Going to the next one, taking the base 1/5, raising it to a power equals 125. Remember what this log means. 1/5 to what power gives me 125. So a couple of things. Just like in the last problem, the only way to change a fraction into a whole number is by using a negative power. So I know that my power has to be negative. And then I want you to think, how do I change 5 into 125 using a power? 5 cubed is 125. So that means that 1/5 to the -3rd is 125. Last one, if I want to figure out this last one, again, that 36 is my exponent base, 36 to the x power. The inside of the log comes the other side of the equal sign. And so I want you to look at the representation here. We're trying to change 36 into the number 6. The only kind of power that will shrink a number is a fractional power. So I want you to think numerically. Some of you might be thinking in your head, well, the easiest way to change 36 to 6 is by taking the square root, and I would absolutely agree with that. Now think about square root in terms of a power. What power is a square root the same thing as? That power is 1/2. So if I take 36 and I raise it to the 1/2 power, I get 6 as the answer, because the 1/2 power is the same thing as the square root. This is something that you're going to have to be able to do without the use of a calculator. I'm not going to let you use a scientific calculator to figure these out because it's not necessary to have a scientific calculator. You can figure these out without one. So let's talk about the next thing. The next thing we're going to talk about is why do we study exponential functions and log functions together? The reason why is that they are inverses of each other. So you can think of it as two ways. They're inverse functions, meaning that they're reflections of each other over the line y equals x, and we're going to look at that regard a little bit later. But the other thing you can look at it as is they undo each other's operations the same way that addition and subtraction cancel each other out, and the same way that multiplication and division cancel each other out, the same way that squaring and square rooting cancel each other out, the same way that cubing and cube rooting cancel each other out. So how exactly does that work? If I asked you to simplify something that looked like this, I want you to ask yourself this question. First, using what we just did numerically. 2 to what power gives you 2 cubed? Well, you might be thinking to yourself, well, duh, 3. 2 to the 3rd power is going to give me 2 cubed. You can also look at this as this is going to simplify by simply that log and the exponent base canceling each other out, and all you get is the power of 3. You can do it the other way around also. Say I have 5 raised to the log base 5 of 4, something like that. Anytime I have an exponent base and log base that are the same number like this, just like I have exponent base and log base of the same number like this, they just simply cancel each other out. So that 5 and that log cancel out because they're the same base number, and all you get is the number 4 as the answer. They undo each other just like every other inverse operation you learned about in Algebra 1 and in Algebra 2. So that means when I come down here, you might be thinking to yourself, well, Mr. E, there's no number down here for this log. Remember, anytime you don't see a number written there, that means common log. That means log base 10. So if you forget that, you can always write a little 10 in there. So if you don't see a number, that means log base 10. So since these two numbers are the same, these actually just cancel each other out, and all you get is the number 4. So moving down to some simpler ones just like that one, looking at this one, notice the exponent base and log base are the same. They just cancel each other out, and all you get is x. Notice that these are the same, log base 7 and 7, so all you get is negative 3x. It seems like it shouldn't be that simple, doesn't it? But it actually is that simple. This one here, just like when we did common log over here, remember when I see this ln, that actually means log base e. So if you want to rewrite this so that you can remind yourself of that, you would write this as e to the log base e of 20. So using the same things that we just did here in these last two problems, if you have exponent base and log base that are the same, they just simply cancel each other out, and all you get is the number 20 as the answer. Yes, the problems are supposed to be that easy. I promise. I'm not trying to play a trick on you. So let's talk about this one here and this one here, because they look a little different. So I want you to notice is these don't cancel each other right away. You don't just get an answer of x because these base numbers aren't the same. But I can make them the same. That 25 can be rewritten as 5 to a power. So think about it for a second as I write this down. 25 can be rewritten as 5 squared. So rather than having a 25 to the x there, you can have 5 to the 2x there instead. So by simply rewriting 25 as 2 squared, they now cancel out, and all you get as an answer is 2x. Same thing down here. 64 and the 2 aren't going to cancel out. They're not the same base. But if you know your 2's well enough, I'm hoping you can tell me that 64 is 2 to the 6th power. So I can rewrite 64 as 2 to the 6x. Now that they're the same base numbers, log 2 and exponent base 2, they now cancel each other out, and all you get as an answer is 6x. So we can use the fact that these two things are inverses to help us simplify some expressions that are actually pretty easy to simplify. So a couple more, just so you're aware, if we have something like 5 ln of e to the 7th. Okay, well this 5, nothing's going to happen with this right now, so I'm not even going to pay attention to it. But what we should realize is ln is log base e, and I've got exponent base e. Those are simply going to cancel out, and all you're going to get for an answer is 7. Now, what do I do with the 5 and the 7? Do I add them? Do I multiply them? What do I do? This means 5 times natural log e to the 7th. So when I bring these down, we're not going to add them together. We're going to multiply them. 5 times this answer. So 5 times 7 would give me an answer of 35. Next thing we're going to talk about, since they're inverses of each other, let's actually find the inverse of some logs and exponentials. So if I start with an exponential, if I want the inverse, your end is going to be a logarithm. So if you start with exponential, end with log. And the reverse is also the same. If you start with a log, you're going to end with an exponential. So if you start off letter B here as natural log, and then you tell me the end answer, the inverse, is a natural log, you've done the problem incorrectly. If you start with the problem as an exponential base 6 and you end with an exponential base 6, you've done the problem incorrectly. If I start with an exponential, I'm going to end with a log. So anytime I find the inverse, remember, main objective with this, switch x and y. So that's the first step. What you want to do is solve the equation for y. So then first thing I'm going to do here is I'm going to add 3 to both sides. So I get x plus 3 equals 6 to the y plus 5. Now your goal to solve for y is to get that y isolated by itself. Well, it's impossible to do right now because the y is in the power. So what I want you to think about is, right now it's in exponent form. What if I changed it into log form? So if I've got exponent base 6, remember that's the same thing as writing log base 6. Well, what goes inside the log? The other side of the equal sign goes inside, and the power goes down on one side by itself. The only thing you'd have left to do to solve for y is to subtract 5. So I would get y equals log base 6 of x plus 3 in parentheses, and you would subtract 5 as your last step. I started with an exponential, I ended with a logarithm. Now let's talk about letter B. Letter B over here, switching x and y. There's no number hanging out here, so I don't have to worry about adding or subtracting anything yet. You can't do anything with what's inside here until they're unattached from the logarithm. So I want you to think about this. This is log base e. So if I want to change this into exponent form, I would use exponent base e. The other side of the equal sign becomes the power. The inside of the logarithm is now freed up. So exponent form, log form. You can switch back and forth between them both. Last thing to solve for y, subtract 3 from both sides. So y equals e to the x minus 3. Skipping down, first thing I do here, switch x and y. Once I've done that, again, you want to look at this and make sure you know that that's log base e. So some of you might want to rewrite it that way. It's never a bad thing to have too much information. Now there's nothing hanging out here, so I don't have to worry about adding or subtracting anything. All I'm going to do is change this into exponent form. Log base e becomes exponent base e. The other side of the equal sign becomes the power. The inside of the log is now freed up. Last thing I'm going to do, add 5 to both sides. Y equals e to the x plus 5. Last one, start with an exponent, end with a log. First thing, switch x and y. In order to get y freed up, I need this 2 base by itself, so I'm going to add 3 to both sides. And then I need to get this so that it is not in exponent form anymore, so that it is in log form. So this is an exponent base 2, which means I'm going to use log base 2. The other side of the equal sign goes inside the log, x plus 3. And now the power of y is freed up. And there's your inverse. Start with an exponential, end with a log. Start with a log, end with an exponential. Start with an exponential, end with a log. Start with a log, end with an exponential. Last thing we're going to talk about. What do these things look like on a graph? So here's what I'm going to draw attention to. Number 1, there's 2 graphs on here. Reason why? This one here is an exponential function. That would be like y equals 2 to the x. On this graph, this one here is an exponential function. It's an exponential decay. that would be like y equals 1/2 to the x. Notice that I've got the line y equals x drawn in here, and the reason why is because an exponential growth is the inverse of a logarithmic growth. So this would be like something like y equals log base 2 of x. I've got the exponential decay drawn in with a logarithmic decay. This would be something like log base 1/2 of x. And again, notice the reflections. Above the line y equals x, the logarithm is below. This portion is above, that portion is below. This portion's above, that portion's below. Everything is flip-flopped over the line y equals x. So what we're going to learn is that all of the translations and transformations we've talked about, sliding left and right, sliding up and down, reflecting and shifting, all of those things follow the same rules as all of the other translations that we've done. So anything messing with the x is going to slide you left and right. Anything on the outside is going to slide you up and down. Anything, a negative on the outside is going to flip you upside down. And anything on the inside of the parentheses is going to flip you horizontally, so over the y-axis. So we're going to do a couple of graphing problems, and that will be it for the video. So, number one, if I want to graph log base 4 of x, we're going to treat this a little differently than what you'd actually probably expect. Number one, I don't want to graph things in log form because log form is new for me. Well, not new for me, but new for you. So the first thing I'm going to do is I'm going to switch it into exponent form. So the exponent form of this would be 4 base to the y power equals x. And what we're going to do is we're going to make an xy table based off of the exponential form. So let's talk about that. If we're graphing an exponential, we're going to graph the exact same numbers that we graphed last class, -1, 0, and 1. Now here's the deal. Notice what letter is in the exponent. So instead of graphing -1, 0, and 1 as the x's, we're going to completely change course, and we're going to graph them as the y coordinates. Now I want you to think about the concept of inverses. Inverses flip-flop x and y. So in an exponential, those three numbers are the x column. In a logarithm, those three numbers are the y column. That's the whole concept of inverses. So let's fill in the table then. If I plug a -1 in here, remember, number to a negative power is not a negative number, it's a fraction. So 4 to the negative first is 1/4, not -4. 4 to the 0 is 1. 4 to the first is 4. So let's see what this thing looks like. 1/4 down 1 would look something like that. 1, 0 is an x-intercept. And 4, 1 looks like that. So this is going to slowly grow, and it's going to dive very quickly. Now, why is the y-axis a vertical asymptote? I want you to think about an exponential. Exponentials had horizontal asymptotes. Logarithms are the inverse, so everything flip-flops. So logarithms are going to have vertical asymptotes. Also, we'll talk in class about a really, really important thing about negatives inside of a log, and we'll probably save that discussion for in class. So what am I going to do now? I have this, and that's great, but I'm actually trying to graph this thing. So what do? I'm going to make an XY table based off of the one I already made using the shifts here. A +1 takes me left, and -2 takes me down. All I'm going to do to move left is subtract 1 from all of these numbers. Subtracting 1 here is going to give me a -3/4. Subtracting 1 gives me 0. Subtracting 1 gives me 3. A down 2 is going to take me down in all of those directions. So I'm going to subtract 2 from that, -3. Subtract 2, -2. Subtract 2, -1. Now here's the last thing we have to identify. Since a logarithm has a vertical asymptote, that means that as the graph shifts, the asymptote is going to shift with it. But what direction will it shift? With an exponential, your horizontal went up and down with the graph. With a logarithm, your vertical is going to go left and right with your graph. So this one is going to have a new vertical asymptote, left one, which would be at -1. So I'm going to graph that vertical asymptote at -1, and then graph my points. -3/4, -3. So I'd be down here, 0, -2, and then 3, -1. So I'm going to have the same shape. It's just been shifted left and down. Last thing, domain and range. Logarithms will never stop going up. They'll never stop going down. So range is the all real numbers now. Domain, it never goes past -1, but it goes forever to the right. So from -1 to infinity, we're never going to hit that vertical asymptote, so we're going to do an open parenthesis. All right, last problem. Again, first thing I'm going to do, put this in exponent form. So that would be the same thing as 1/3 to the y power, because that f of x is a y, and that equals x. Making a table based off of that, same 3 values as an exponential, but again, we're picking them for the opposite column now. If I throw -1 in, you get a value of 3. If I throw 0 in, you get 1. If I throw 1 in, you get 1/3. So now let's look at what this thing looks like. 3, -1 would be down here, 1, 0, and then right 1/3 and up 1. So this one is going to look just like the logarithmic growth, except it's going to be flipped upside down. So this is going to go sky high really fast, and it's going to dive very slowly. This one dove really fast and went sky high very slowly. So everything is flip-flopped. All right, let's identify our shifts. We're going to go to the right by 3. So that means that the y column isn't going to change at all, because the only thing that's happening is we're going to the right. So all of these numbers, since we're going right 3, we're going to add 3 to all of them. So we've got a 6, a 4, and a 3 and 1/3. Not only has the entire curve shifted to the right, but so has the vertical asymptote. That follows the graph. So x equals 3. 1, 2, 3. And let's plot our points. 6, -1. 4, 0. And then 3 1/3, 1. Same shape. Same level for my y values. The only thing that's changed is we've pushed the entire graph to the right by 3. Domain and range. Just like with a logarithmic growth, your logarithmic decay never going to stop going up, never going to stop going down. So my range, all real numbers. Domain, we never go past that vertical asymptote boundary. So positive 3 is the furthest we go. And then we continue to move off to the right forever, so to infinity, and both are going to be open parentheses. Make sure you write down questions that you have so that you can ask about them in class.